All right, we're going to look at one more problem together here today before you begin to do some practice problems on your own. And this problem puts together all of the things that we have talked about in this lesson so far today. It addresses the area of a force versus displacement graph. It uses the work energy theorem, and it also addresses kinetic energy. Now, I'm going to do this video in a couple parts because there's some really key ideas here that I want to make sure that we don't forget about. So let's just take a look at the scenario that we have going on. So to start, we have a 5 kilogram object sliding across a horizontal surface due to the net force acting on it. That net concept that this is a net force is super important because that means we can use the work energy theorem to do most of the problem solving for us here. And it does tell you that at x equals 0 meters, the object is moving with a speed of 2.8 meters per second. I'm going to go ahead and just make us a note of that at this exact moment, this green line that I've drawn, we are moving at 2.8 meters per second. Again, being able to label some things and give yourself some clues as to what's happening is super important. So we've got a graph. We'll come back to the graph in a second. Let's just look at the questions that we have at the bottom though. Question 1 is how much kinetic energy does that object have at 0 meters? So at the point where it's traveling at 2.8 meters per second, can we calculate how much kinetic energy it has? The second question, how fast is the object moving at x equals 20 meters? That's this point here. We want to be able to figure out how fast the object is moving at this point. So I'm just going to label and give us just sort of a clue and a thing to look for later on. The last question here, how fast is the object moving at x equals 30 meters? So again, looking at this 30 meter mark and being able to recognize that that's another thing we're going to have to solve for. How fast is it moving at this particular point? Now let's look at the graph as a whole because there's a couple things here that I want to make sure that we point out. There is a force acting on this object at all points in time, and it is always a positive net force because all of those force values are above the x-axis. All that happens is it is a constant force from 10 to 20 newtons, which we're used to seeing. We can handle that. But then from 20 to 30 meters, the value for that force decreases. It'd be like you were pushing an object forward and then you kept pushing it forward, but the amount, how strong you were pushing, you decreased until you weren't touching it at all. That object's going to keep moving forward. It's going to keep experiencing a force. You're just not going to exert as much force on the object. At no point is it changing direction. But this is a graph of force versus displacement. And similar to graphs of velocity versus time that we saw before, remember that the area of this graph is a very useful piece of information because the area of a force versus displacement graph gives you the work that is done. And specifically what's happening here is that this area just between 0 meters and 20 meters will give you the work that is done from 0 meters to 20 meters by a 100 Newton force. The same is true as we go here from 20 meters down to 30. If we calculate the area here, it's going to give us the work that is done in moving the object from 20 meters to 30 meters. So those skills still transfer. All I want you to do right now is pause and go ahead and calculate the areas of these two sections. Calculate for me the work that is done from 0 to 20 meters, and then the work that is done from 20 to 30 meters. Go ahead and pause the video, try it on your own, come back and check your answers in a second. Okay, we know that the area is the work that is done. This first section here is pretty straightforward because it's just a rectangle. So the area is going to be base times height. So 100 newtons is my height. My base is going to be 20 meters. We get here then that the work being done, 2,000 joules. We can do the same thing for that triangular piece here, just remembering that the area of a triangle is 1/2 base times height. So 1/2 times 100 newtons times a base here of 10 meters is going to give us a work done here of 500 joules. Now notice those are both positive values for work. What that's telling us is that from 0 to 20 meters, my object is going to be increasing in energy. From 20 to 30 meters, my object is going to be increasing in energy. It's both positive work. Energy is being added to the system. You could even take this one step further and you could calculate the net work done on this object from 0 to 30 meters and get that it's 2,500 joules. Lots of information we get about the work that's done. So this video is going to end here, and the next video is going to pick right back up with actually solving the problems. But take a minute and just process what it is that we just did before watching the next one.